Hi, everybody. Good evening, and thank you for taking the time out to attend our talk. My name is Anahita, and I'm joined here by my colleague, Dina. We're both from Intel. I'm a senior software engineer with the AI products group at Intel, and we're going to be talking about a distributed end-to-end drug similarity analytics and visualization workflow using Apache Spark, of course. A quick introduction about who we are. We belong to the Intel Nirvana AI products group, like I mentioned. So Intel does a lot of stuff in artificial intelligence, ranging from experiences like autonomous driving to drones to VR to toolkits like the Intel DL training deployment, the Intel Nirvana deep learning software and cloud. That's the team we're part of. A lot of framework work as well, like optimizations. On the Apache Spark side, Intel is a major contributor to algorithms for machine learning, like MLlib contributions, optimizations on Intel architectures, and also the big DL, which is deep learning on Spark. There's also the Nirvana stack of products, and I'm not going to get into those right now. There's also optimizations for Theano, Caffe, Torch, and MXNet. And there are also libraries like Intel Python distribution, Intel DAL distribution that just give optimization on Intel architectures. And of course, hardware. So what we plan to talk about today, just a brief overview. What exactly is chemical similarity? That's kind of the title of our talk. I'll go over the use case and give you an overview of the problem we're trying to solve. Introduce you to our data, which is drug data, and what is SMILES. When you're talking about similarity, the coefficient that we're going to be using over here, that is the Tanimoto coefficient. How graph analytics can be used to uncover insights, and how Spark is very powerful in helping us doing so, and the algorithms that we've implemented and open sourced on Spark. Why Apache Spark was a natural choice for us to do all of these mentioned things. Then also talking about the library. SparkTK is a library that we've developed at Intel, and it's open source like I mentioned, so we'll get an overview of that. And how we can visualize using Superset, which is Airbnb's visualization tool, and also a demo and future steps. Okay, so when it comes to chemical similarity, like the name suggests, it's basically understanding or the study of the similarity in chemical elements. It could be either element similarity, molecular similarity, or similarity within chemical compounds. Similarity could be of two types, structural or functional. When we say structural, it's basically the structure of the molecule or the compound. For example, whether it's similar in carbon, hydrogen, oxygen combinations, or whether it's functionally doing the same thing, maybe reacting to the same thing, or maybe having similar properties. So those are the two distinctions. You might wonder why this is useful. This has varied use cases, some of them including you might want to predict the chemical properties of certain compounds. So if you know chemical A and chemical B are similar, and you know the characteristics of A, you can predict something of another drug. Or designing chemicals with predefined set of properties. In today's day, we're constantly finding new medications, new cures, new compounds to do a lot of things for us. So designing this is very useful in understanding how drugs relate with each other and drug design. So brief overview of our use case. We start with raw drug data. Now, to derive any kinds of insights, if we just have a chemical composition like carbon, hydrogen, oxygen, nitrogen, I can't really do much unless I represent it in a format that a model or an algorithm can take in. Also, it comes into the consideration if you have vast amounts of data, storage and representation is very crucial. So we talk about how we can go from drug data to an internal representation or storage. Then comes the similarity part. How do we identify if two drugs are similar? So defining a metric or a factor for differentiation. Once you have that, then you can derive insights. What do we mean by deriving insights? It could mean multiple things, not just limited to the 4 boxes below. For example, you might want to say which drugs are similar to each other. What are side effects? So studying of side effects, you might realize that a person is allergic to these, or side effects are caused by these drugs. And then if you understand these two drugs are similar by this metric, then you're likely to have those reactions to another drug as well, which is highly similar. Maybe also studying drug creation and combination, like I mentioned previously, to find new cures, to invent new drugs. Possibly even extending this to recommendations. For example, if a patient has these symptoms and we identify that it is, say, disease A or disease B, possibly even recommending drugs. Okay, so those of you who are familiar with bioinformatics, SMILES is basically a method used to like a string representation for a drug or for a compound. So it stands for Simplified Molecular Input Line Entry System. It's basically coming up with a string for each drug. So it's a very commonly used database which has a big list of drugs or compounds or molecules and their representation. So what you see is the name of ethane, and the SMILES string associated with it is CC. Similarly, acetic acid is represented by the string over here. So it's just basically a typographical method using printable characters for molecules and their reactions. So the input in our demo and our talk today is basically this. We started off with raw drug data. So you could see we have a chemical ID on the leftmost column, followed by the drug name, so like levodopa, nipoctic acid, so on and so forth. And then we had the corresponding SMILES index. What you see to the latter right columns, you have a lot of chemical data sets like drug bank, PubChem. What is their ID in that data set? Because sometimes biologists or chemical engineers might be interested in looking this up in this respective data set and study its properties. For our demo, we are only concerned with the name of the drug and the SMILES index. So like I mentioned, the SMILES index or the SMILES index is basically a string, and we know that we can't really do much with string in this case, so we kind of had to get it into a numerical representation to derive insight or make sense out of it. So what we used is we used a coefficient called as the Tanimoto coefficient, which ranges from 0 to 1. So if I take drug A and drug B and I compute the Tanimoto coefficient of them, the higher it is or the closer it is to 1, the more similar the drugs are. Basically, the Tanimoto coefficient just acts as a ratio over bitmaps. So that's the equation that follows it at the bottom. And you're free to look up the Wikipedia link on more information on it. Basically, each bit that you're coming up with represents the presence or absence of a characteristic. Okay, so we spoke about the data. We spoke about coming up with a metric that is a Tanimoto coefficient to kind of understand the similarity between drugs. The next thing I want to talk about is graph analytics and how this can be useful. Graphs are basically mathematical structures used to model pairwise relations between objects. In this case, our objects are, say, any two drugs, and the relation can be interpreted as the Tanimoto coefficient or the similarity metric. Graphs are very powerful because they can help not just model, but also a lot of algorithms can be run over them to derive insights. So basically, the vertices or the nodes or the points, whatever terminology you use, can be used to connect nodes, and the edges or the arcs could mean different things. In our use case, it means the similarity coefficient. Again, on a broader sense, just introducing this, if you're not familiar, you could have directed edges or undirected edges. Directed is very specific, going from drug A to drug B. Undirected is it's equal both ways. Extending this is also weighted and unweighted edges. In this case, we're going with a weighted graph because the similarity metric between A and B could be very different from A and C. So we have weights associated with each edge. If you do not, then it's a uniform weight. Then you could say it's unweighted, where everything has a uniform weight. Okay. I'll quickly go over some of the algorithms that are present and how graphs can be used to derive insights out of these. All of these algorithms have been implemented by us in GraphX. They're all distributed implementations, and Dina will walk us through the library that has it. But I'll just introduce the concepts first and walk you through some of the questions each of these algorithms can help answer. So the first one is connected components. Using connected components, you basically form subgraphs in which any two vertices are connected by edges. For example, you can see in this figure, we very clearly have just 3 connected components. Over here, there is going to be no overlap between component 1 and component 2. So there's going to be no edge going from any node in component 1 to component 2, so on from 2 to 3 or 3 to 1. So what this can tell me, if I run this connected component algorithms on any graph, in this case, it's going to tell me what clusters of similar drugs do we have based on the Tanimoto coefficient of similarity. The next algorithm is clustering coefficient. It's basically just going to tell me the measure or degree to which nodes in a graph tend to cluster together. For example, you could have 2 types of clustering coefficients, global or local. Global deals with the overall indication of clustering in the network, whereas local is just considered with that individual network, for that individual subgraph. So you might want to see how close is this graph or the subgraph to being a clique. If you're familiar with what a clique is, it's basically all nodes in the graph connect to each other. So that's local when you're dealing with a local subgraph. So we might want to just run this over our graph data to just understand numerical metrics of our graph, to kind of understand how clustered this is together or how sparse is it, is there a lot of high similarity in the data or not. Another commonly used algorithm is the label propagation algorithm. So if you're not familiar with the concept of communities, the community structure is basically, it deals with the idea that if the nodes in a graph can be easily grouped into densely overlapping sets, that's when it forms a community. So two things, it's a dense representation and there could be overlap, unlike the previous ones which didn't have an overlap. So the principle follows over here that the pair of nodes are more likely to be connected if they are both members of the same community. Label propagation has very efficient runtime, so people prefer using this for multiple occasions, and it requires no a priori information about the network when you're needing to run it. You might want to study with this communities in the drugs. The next algorithm is closeness centrality. It basically deals with understanding what drugs are most similar to the others. The more central a node, the closer it is to the all other nodes. So it's basically a very simple equation. It takes the average length of the shortest path between the nodes and all other nodes. So given drug A, I'm going to compute its shortest path to all of its nodes. So if the shortest path is basically maybe a sum of each of the metrics, or maybe I could take a weighted sum, so on and so forth, and then taking the average of that gives me the closeness centrality. So there are typically three centrality algorithms. Closeness is what I spoke about. There is betweenness, and the third one is degree. So coming to the second one is betweenness centrality. As the name suggests, you're kind of trying to understand which drugs stand between each other. So you quantify the number of times a node acts as a bridge along the shortest path between two nodes. Why this is important is because if we realize that we have very high betweenness centrality, one drug could influence a lot of drugs along the path, maybe finding some issues with that drug, or finding a cure to that, or finding a reaction to that has implications on other drugs. So vertices that have a high probability to occur on a randomly chosen shortest path have high betweenness. So like you can see in the figure, the ones on the red don't really come in between, or don't really act as a bridge between other two nodes, but as you go closer, the green and the blue ones are very strong in betweenness. And the last algorithm I'm going to be talking about is degree centrality. That's the one we've used in our demo, and we'll show you how we've used it to derive insights. This helps us understand which are the most influential drugs or most influential vertices in this graph, for example. So it's pretty simple. Again, over here, we're just kind of studying the number of edges incident upon a node. It studies the immediate risk of a node for catching a network flow, for example, in a social network or in a state of a biological network. They're very important over there. And in directed graphs, they can study two things, the in degree and out degree. In degree deals with how many edges are incident upon a node. Out degree talks about how many edges arise out of a node. So to solve all of these problems, why did we choose Apache Spark? Because of the following reasons, and this basically describes what Spark ecosystem is. Because of the Spark core for the beginning, because of the distributed nature that it helped us handle, we didn't have to worry about distributing it. We didn't have to worry about how the RDD parallelizes stuff and all of that. So Spark handled it for us, and we could focus more on the solution and implementing the algorithm that we needed. Spark SQL with the Catalyst optimizer that we've seen is very powerful. It's also useful for querying, so that was very powerful again. What we mainly used for this is graphics, because we implemented all of our algorithms on graphics, and like I mentioned, they're open source, so you're free to check them out and use them. And it basically gave us the foundation that we needed, and we could just develop a smart distributed algorithm over it. MLlib that we know provides a lot of functionality for classifiers, regressors, and clustering, so that can be used as feature engineering techniques as well. And of course, Spark streaming, when you have incoming data, for example, if we've built a graph and we get a new drug that comes in, streaming data can be handled to maybe test the metrics over there to compute the new Tanimoto coefficient between that drug and all other drugs in the graph. So now I'd like to introduce SparkTK, which is Spark Toolkit. It's a library that we've worked on. It's an open source library enhancing the Spark experience. When I mean enhancing, it means we've added APIs for feature engineering. We've added ETL, we've added graph construction and algorithms, machine learning and scoring. We've provided an abstraction level familiar to data scientists. Most data scientists prefer using a table or a frame. They're not really concerned with what an RDD is or a data set or a data frame. So if you're one of those people who don't want to worry about too many of these distributed processing techniques, You just think of it as a frame in SparkTK, and we handle the conversion under the hood for you. But if you're a Spark expert, like probably most of you are, you can still leverage Spark APIs, which are seamlessly exposed, and you can run it as standalone Spark by itself. And in real-world applications that we've seen, we have multiple components that go in together to build an end-to-end solution or a demo or a app. So it's very easy to build apps, plugging in other tools or libraries, like Tina's going to show us in just a minute. And we've seen over here, we might need a visualizer, we might need something for scoring, we might need something for machine learning. And that's the link to the GitHub page if you're interested in checking it out. And the second link is to documentation. And I'll now like to call upon Dina to walk us through some of the components and the rest of the demo. Thank you.
So the first component that I'm going to go through is called frames. It's a scalable data frame representation, and it's also the main data structure that's used by SparkTK. Frames strive to be more intuitive than low-level HDFS files and Spark data formats. They provide the ability to infer the schema based on the data being imported. Frames have an easy-to-use API that allows for manipulating the frames of data for feature engineering and exploration using methods such as joins and aggregations. As an example, you could specify a column to group by and then get statistics such as counts, averages, minimums, and max. It's also the data structure that is used as inputs to all of our models. It's easy to go from SparkTK frames to Spark representations such as RDDs and data frames, so that could then be used with other libraries. The next component that I'm going to go through are graphs. SparkTK creates scalable graphs using frames of vertices and frames of edges. We have distributed graph algorithms that have been developed in-house using GraphX. These are the ones that Anahita just went over. SparkTK supports importing and exporting to OrientDB, which allows for easy visualization as well as real-time graph querying. Both SparkTK and OrientDB are able to store massive graphs. SparkTK includes many machine learning algorithms as well as streaming capabilities. We have a list of them here, and they include time series analytics algorithms such as ARX, ARIMA, and ARIMA-X, recommender systems like collaborative filtering and dimensionality reduction, topic modeling using LDA, clustering using k-means, classification and regression using logistic regression, random forest classifiers, naive Bayes, and SVM. We also have in-house image processing with DICOM medical imaging, such as CAT scans and X-rays. We also support scikit-learn models, and we have a scoring engine that allows for doing streaming predictions with a REST endpoint. One of the third-party libraries that we use is called DKit. It's an open-source chem informatics and machine learning library that's written in C++ and Python. For our demo, we use DKit's Python API to calculate the similarity between two drugs. To do this, we started out with the SMILE string, which describes the chemical structure of each drug, and then translated that into DKit's molecule object, which is called a mole. Using the mole object, we are then able to calculate the similarity between the two drugs. DKit offers several different similarity functions. We ended up using the default, which is called the Tanimoto coefficient. SparkTK also allows for importing and exporting from several different sources, including CSV, HBase, JDBC, Hive, JSON, Pandas, and OrientDB. For all of these sources, it's a really easy import or export function, such as import CSV, export to CSV, import to Hive, export to Hive, etc. SparkTK frames are also easily able to go from Spark objects or from SparkTK objects to Spark objects like RDDs and data frames. Superset is a visualization tool which we use. It's developed by Airbnb. It was previously named Panoramics and then Caravelle, but now it's known as Superset. It allows for getting data from a variety of sources. In our demo, we're using a Postgres database. After Superset's connected to the database and its tables, you're easily able to create a dashboard of visual objects, which they call slices. Slices can be tables of data, directed graphs, various types of charts, and even maps. Okay, Before we get into the demo, here's a recap of the use case that Anahita talked about earlier. We're going to start off with raw drug data, import that into SparkTK. That'll be represented as a frame. Once we have it in a frame, we'll be able to clean up the data by dropping out columns that we don't need and joining it with another frame so that we have our data organized in such a way that we can compare one drug to another. After that, we'll use our DKit to calculate the similarity between the two drugs, and then derive insights using graph analytics, and then do visualization using Superset. So I'm jumping here to a Jupyter notebook. This is running on a workstation back at the office. The first thing that I'm going to do is import the different libraries that we're using. So we'll import our DKit as well as SparkTK. Initializing SparkTK is really similar to initializing Spark. We create a TK context, which is really similar to the Spark context. We're really like just creating the Spark context under the hood. I'm passing it some class paths to Postgres since I'll be using that later, as well as a Spark config file. So next thing that I'm going to do is get our raw data into SparkTK. So I have that stored in a CSV file, and I'm using SparkTK's import CSV function, giving it the path to that drugs.csv file. I'm telling it that the delimiter is a tab and that it has a header row. Since I haven't specified the schema, it's going to use the data from that CSV file to try to assume the data types. So it found that the first column, which is the ID column, is an integer, and the rest of them are strings. Since the thing that we really care about are the drug names, ID, and smiles index, I'm going to go ahead and drop all the columns that I don't need. I'm then using SparkTK's inspect function to take a look at what data is in the frame. By default, this shows the first 10 rows of data, and you can see the columns are ID, name, and smiles. So now that we have that, we're going to go ahead and try to calculate the similarity between the drugs. And to do this, I'm going to import another frame that's called drug or edges frame. And this contains the top 20 connections for each drug. To start out with, we were comparing every drug to every other drug. But for the simplicity of this demo, I'm just going to create a frame with the top 20 connections for each drug. So again, I'm using SparkTK's import CSV function, giving it the path to my CSV file. This time I'm specifying a schema, and again, we have a header row and the delimiter is a tab. I'm using the inspect function again so you can see what the data looks like. I'm printing out a count of both the edges and the nodes. You can see that we have roughly 1,200 nodes and 25,000 edges. Next, what we want to do is organize the data so that we have the frame with the smiles index for both the source and the target. So I'm doing a join on the nodes frame for the source, as well as a join with the nodes frame for the destination. Then I'm renaming some columns just to make it easier to understand. I'm doing an inspect on that joined frame, and we can see that we have the target name, target smiles, source name, source smiles, and then the two ID columns. So now that we have that joined frame, we're ready to actually calculate the Tanimoto coefficient. I've defined a function called calculate Tanimoto, which takes in the two smiles indexes for the two drugs, and then uses our DKit to get the molecule object for those two smiles indexes, and then uses the fingerprint similarity function to calculate the Tanimoto coefficient. SparkTK has this add columns function off the frame, which then goes ahead and calculates a Tanimoto for every row. I'm also adding a column called rounded Tanimoto in order to create a histogram later. So here I'm using the inspect function again. This time I'm specifying to show 20 rows as well as only specific columns. So we see the source name, target name, along with their Tanimotos. Again, remember that the higher the Tanimoto, the more similar the drug. So next I'm going to show one of the graph algorithms. And in order to do that, I need to create a graph object in SparkTK. I'm going to use the same node frame that I created earlier, but I'm actually going to import a new frame for the edges. This one has all the drug edges that have a Tanimoto coefficient greater than 0.4. So I'm importing that file again using import CSV and showing you what it looks like. So we have the source, destination, as well as their Tanimoto coefficient. So now I can create the SparkTK graph using the nodes frame as well as that new edges frame that I just created, and that gives us back a graph object. From that graph object, you have access to all the different algorithms that Anahita previously talked about. Here I'm going to show degree centrality and specify the out degree. I'm going to sort on the degree centrality column descending so that we can kind of highlight which drugs have high Tanimoto connections. So the last thing I'm showing here is that we're going to export the data to Postgres so that we can then use it with Superset. So the frames have this export to JDBC function where I pass it the path to my database as well as the name of the table. Then the last thing that I'm doing is I'm importing that Superset library and then kind of setting it up in Superset. So I'm calling the create table function with the joined frame as well as specifying my database name and the table name. So now I'm going to jump over to Superset and kind of show you what it looks like. They have different data sources. Here I'm showing you the list of databases that I've connected to Superset. You can also take a look at the different tables. So the one that I just imported was drug graph 2. They also have some security features, so if you want to list out which users and different roles and who has access to what data, you can do that here. Slices are all the different visual aspects of the dashboard. This is a drug dashboard that we've created. It has a visual of the actual graph as well as some tables showing what the Tanimoto coefficients are. Here's the histogram that I created using that rounded Tanimoto that I created a column for, as well as like other tables printing out like the connection count, as well as a smiles index. So what I'm going to do is filter here on a certain drug. I'm going to search for levodopa. And the filter affects all the different slices on my dashboard. So you can see that the drug graph changed. You can just see levodopa as the source, and it shows all of its targets, along with all the other components like this table, the histogram. The connection count's now 20 since I had done top 20 earlier. And this table at the bottom is also filtered. So next steps and thoughts on how we can take this further. We could use additional data such as known drug side effects and implications of drug interactions to derive more insights. For example, do drugs that are highly similar have similar side effects? Or if drug A is dangerous to combine with drug B, and we know that drug C is really similar to drug A, is that also dangerous to combine with drug B? This type of information could be useful when creating new drugs. We could also use electronic patient records and train models to try to predict things like what drug a particular person should try to avoid. We can try to derive things like drug recommendations as well as suggestions. Thank you for attending our presentation. Here's a couple links. First, we have a link to our GitHub page. SparkTK is open source. The second link is a link to our documentation for our API. We have both a Python API as well as a Scala API. Yeah.